Hello, we're looking at Biology Practical 2, investigating osmosis in a potato. So you're looking at putting your date in here on the little sheet stuck inside the front cover of your red book. Nice big title page so that you can see which practical you've been doing and when you've been doing it. And remember that this is 15% of the GCSE paper that you're going to sit in Year 11. So it is pretty important to make sure that you get this right. So when you're looking at these practicals, there's various different bits you can be assessed on, so you need to make sure that you're aware of the practical overall and not just the little bit that you focused on in class. So in this one here, we're looking at putting some potato tissue into different concentrations of salt solutions. The key science for this bit is looking at osmosis. Knowing your definitions from your lessons is important for this one. It's the net movement, so that's some's moving from one side to the other and vice versa. But it's the total movement. Is it moving into the potato, out of the potato, or is it generally staying as it is? It's involving water molecules, and we're looking from a high concentration of water to a low concentration of water through a partially permeable membrane. We're investigating how salt solutions might affect that, so how you might get the salt changing the direction that the water moves. Osmosis is going to be happening across a partially permeable membrane. Remember, that means that the membrane has got small holes in it, so small soluble molecules can fit through, but larger molecules can't, just like in the lining of your small intestine. So you're going to investigate how different concentrations of salt affect how the water's moving through that. The hypothesis that you're testing, which is kind of like an idea with a prediction, is that when the concentration of the salt solution changes, the mass will also change. You could be asked to come up with that sort of idea. You might have to be specific and say, as I increase the salt solution, I'll expect that the mass will increase or decrease, whatever your science makes you think. As long as you're being specific on it, saying, as I make this one bigger, I'll make this one smaller, or something like that. That's one we've given you today, so we're not assessing that. Another thing you might get to do in the exam itself is a really nice one: write a method, or write some equipment that you'd need. So obviously, we're not assessing that on this one. You can see the equipment you'll need for this one. And there's a nice sensible method here. When you're writing a method yourself, remember you've got to use it in a nice logical order. So you've just got to imagine yourself there doing this investigation and picture what you're doing at each step. And when you're measuring something out or using a piece of equipment, you explain what you're doing with it. You don't have to say, I will get my equipment, I will go to the back of the room and I will, measure out this. And it's nice and short and sweet, just like the one here. So in this case here, the first thing that you do is you go to your potato, you'd start boring out some of the cylinders. You use the cork borer in the picture there. So this you just poke through. You've got to make sure that you're poking through nice parallel lines to make sure that you get an even amount of potato. If you keep stabbing through each different way, diagonally, each time you'll have a hole in the middle of your cork bore length, so it's not very good. What you're going to need is not 4 of them, you actually need 6 of them for this one, so I've updated that sheet since I made this PowerPoint. And you're going to be cutting them to 4 centimetre lengths, so make sure you use a ruler and a scalpel. When you're thinking about these things, it does lend to thinking about the investigation later on. If you didn't cut it to 4 centimetres, what would be wrong? If you didn't use your ruler, if you didn't cut it vertically, it might mean it's not the same length, which might mean that the diffusion happens faster or slower, the osmosis, which might cause anomalous results, might cause errors. So we want to try and avoid those as much as possible. So you have some boiling tubes filled with some solutions which you've labelled, going from distilled water, pure water, along through 0.2, 0.4, 0.6, 0.8, 1 molar solutions. Before you do anything, you're going to weigh the mass of your potato and record that on your results table. That'll be on your sheet that you've got. We want to know how much the potato weighs at the start, and then we're going to look at how much it weighs at the end, and then we can work out if water's gone into it or been lost from it by the mass change. So then you're going to carefully measure out your 25 millilitres of solution, which is missing from this method here, which would cost Mr. Prescott, who wrote this, a couple of marks, but we'll let him off on this occasion because he's helping you out. So you measure out the same amount of solution each time, 25 millilitres. If you don't use 25 millilitres each time, you've had less, then there might be less osmosis happening, which is going to be an anomaly. And once we've done that, we can put the potato in the tube and make sure we start them all at the same time. If you left them longer, obviously more chance for osmosis, more chance for a mass change, so we want to make sure we're keeping that nice and fair. And you notice it's nice and clearly labelled with the solution and some initials on it to make sure you know what you've got in it and everything when you come back. Leaving it for 30 minutes is a good time. You might leave it longer or shorter as long as it gives this process a time to happen. Remember, it is passive, it doesn't take energy, so it is going to take a little while. Another thing about making it a fair test, look, the potato, once you've taken it out of the solution after 30 minutes, we're blotting it dry, we're putting it on paper towels because the water on the outside of it weighs something. So even if you just dipped it in for 5 seconds and picked it out again, it's going to weigh more unless you dry that water off the outside. And again, that could be another cause for an anomalous result. And then weigh it again. In this case here, I only just dipped it in and took it out, so obviously it's not changed, but that might happen for something on your investigation. One of the other sections then you could get tested on is health and safety. Now this one's quite brief here. Obviously there's a hazard of using the scalpel. The risk is cutting yourself, so to prevent that, you're going to make sure your fingers are out the way and that you're cutting away from your fingers. Are there any other risks? Oh, God. Potato allergy, salt allergy, not really. You don't have to tell me about tripping over bags and things like that. It's risks specific for the investigation that we're looking at. Okay, so on the one that we've got on the bottom that we just looked at, there's the 0.2 molar. So I'd write the first mass there, the second mass there, and I'll take one away from the other here. So here's a table that was prepared earlier, and funnily enough, you may have to draw a results table yourself, which to me, it's easy marks. When you're looking at the writing down the difference in mass, it matters if it got heavier or if it got lighter. So if it gained mass, then it's going to be a positive difference. So it might have gained 1 gram plus 1 gram. If it's lost mass, it's going to be a negative difference. And that's really, really important when we're looking at drawing your graph. Loads of people will get that wrong. And again, when you're looking at working out your percentages, it matters if it's positive or negative. So if your change in mass is 1 gram out of a total of 3, it's like any other percentage. You put what you got out of the maximum possible. So if there was a test out of 3, that's what you started with, and then you got a change in mass of 1, so you scored 1 out of 3, so it'd be 1 over 3, and then times it by 100 to get it to be a percentage. If you put it the other way around, you get a number which is over 100%, which would be a bit silly in this case, so you should stop yourself and think, I've done something wrong there. So we get the difference in mass, in the numbers I've been using, the 1 gram, down here, the difference in mass, and we're dividing it by the mass at the start, and then times it by 100, and that should give us this number, the positive or negative number. First calculation's dead easy, we're just finding the change in the mass, and it might not have changed at all, remember. So when we're looking at plotting a graph, you need to remember how to do a line of best fit. It might well be that you've got a lovely graph like that, not going to happen. It might well be that you didn't dry a potato or you left it out too long and it dried out, so you got an anomalous result. It might be that one of the potatoes wasn't in the solution fully, so it needs to be weighed down so that it can get that osmosis happening, and this one was left in too long because one of your team left it in too long and forgot to get it out. Maybe the shape was wrong. Either way, you get anomalous results. You're much more likely to get graphs like this, and you don't have to touch each cross, it just has to show the general pattern or trend. The idea of putting in your line of best fit is so that you can go to an area where you've not tested and you should be able to approximate what the outcome would be there without having to go away and do it yourself. You get curves, which are much the same way. You can use a ruler, bend it, nice smooth curve of best fit. Again, you can ignore anomalies if you think they don't fit your pattern, and you're much more likely to get graphs that look like this. The graph today, we gave you the axes because it goes positive and negative. And what you'd be expecting here is that your first ones, where you've not got, where you've got pure water, is where the potatoes are going to get extra mass. So there's my really scruffy point. Yours is going to be better in pencil with a nice neat cross, plotted within 1 millimetre, one little square of where it should be. Your second one should probably be just about isotonic, and then you should get a pattern where it starts going down and down, and then probably maybe even leveling off with a nice smooth curve of best fit. And if you get it wrong, feel free to rub it out and do it again because you did it in pencil. I said a word that you might have not been familiar with there. You might have said isotonic, so I'm just going to nip back for 1 second. So 3 words you might want to use in this bit. Isotonic is where the solution's going to have the same concentration. So in this case, inside and outside the potato, and a lot of time it gets used on sports drinks because it's talking about blood. Isotonic solutions have the same amount of water and salts as your blood. Hypertonic has a higher concentration of solutes, so it might be saltier or more sugary. And hypotonic is where it's got a lower concentration. So in this point here, you may want to label on your graph at this point, oops, let's bring the pointer back. at this point here, it's isotonic, where it just crosses over the x-axis, because that's where the solutions are the same on both sides. So there's no net movement. There's just as much water going into the potato as coming out of it. On the top side over here, we've got that it's hypotonic, so that we've got the solution on the outside is hypertonic. It's got less salt or sugar dissolved in it. So that means the water is going to be moving to where it is more salty or more sugary, which is inside the potato in this case. So the potato has gotten heavier. And down on so that was up here. And then down, once we get into this section towards the bottom, we're looking where it is a hypertonic solution. It's got more sugar or salt dissolved in it than inside the potato. So we've got water moving from inside the potato out of it, which is causing this negative change. Okay? Again, the whole thing on the graph here, the drawing the line of best fit, the plotting it, the axes, all that is something that you could get tested on. So be aware of that. The last little bit is where I've been leading to through a lot of the investigation, looking at evaluating it. So I've discussed the conclusions that we've gone through there. That could be something you tested on. On an evaluation, it's something that may have gone wrong in your investigation, how you'd stop it happening. So here's a good example. The potato chips may float in salty water, like if you ever go to the Red Sea in Egypt, I think it is, where there's loads of salt, you can float dead easily. So you might want to weigh them, all your potato chips down with a drawing pin to make it a nice fair test. If you didn't, the one on the surface hasn't got all the water around the surface, so it's not going to have as much chance for osmosis as the others. So it wouldn't have the same surface area. That's not fair. Another thing you might be asked about is further investigations, what you could do to extend your knowledge on it. So when you're looking back at the graph, one of the things that stands out is you've only gone 0.2, 0.4, 0.6, 0.8. Maybe you want to go in between to find the exact point where it's isotonic. Maybe you want to look at different vegetables to see if turnips do the same thing. It doesn't have to be that you actually want to go away and spend your time doing this, but it's sensible things to extend the knowledge that you've got there, because that's what real scientists do. Once you've found one thing out, you develop it further and keep developing it further when you've got your own specialist niche little area. Okay? If you do have any questions about any of that, if you're not sure about the terminology or any of the skills, make sure you come along and see one of your teachers. Good luck, guys.